this data variable is all about. So let's see what time series forecasting is. So maybe in this data set, what we actually need to predict is not on something that we randomly select as testing. So in the previous one, we randomly divided our data set, but in time series forecasting, we want to divide our data set such that our training data, it contains data from the initial time points, and then we want to predict on the testing data. So mainly, maybe our testing data should be this in this data set. And I plotted how the temperature is varying with the date. So as you can see, there are some seasonal variations. So in time series forecasting, there are different time series models that you can use to get these seasonal variations right. So there are autoregressive models, moving average models, and for seasonality itself, we have Sarema models, so seasonal autoregressive models. Then we have deep learning methods for time series forecasting. So I'll just go through two of them, just a brief introduction of two models. I will be talking about VAR first. And VAR is a model that can be used to discover links between multiple variables that varies over time. So in our data set, temperature is varying over time, and dew point is varying over time, and precipitation is also varying over time. So this in VAR models, it's a bidirectional model. So it has the impact on each other. So predictors influence the targets, and targets also influence predictors. So basically, we can model, say, if this is the temperature, you get your previous temperature values. You also get your previous dew point values, and then you fit a line. So VAR is one method that you can use. I'll move back to our Colab. And let's get back our original data frame, and I'll show you how to split the data. So I can ignore the data cleaning parts. And for this case, I get the data format correct to month, date, and year. And we see how the temperature varies over time. It is the plot that I showed you in the in the presentation as well. So this is how our temperature varies over time. So we see a seasonal pattern, and maybe there looks like it's increasing over time as well, a little bit. So we can ignore the cleaning steps, and we can finally get the data set. And for the data set, we put the index to the date. And now let's get the first 75% of the data for training and the last 25% for testing. So from DF3, we get from everything from the beginning up to the 75. First 75, I get the length of the valley, and I multiply it by 7.5 to get the first 75% of the data, and everything else from here up to the end, the double dots represent until the end for testing. Okay, now we have the training and the testing data sets for our time series forecasting. Okay, so VAR models are little bit difficult to explain. So I keep all the code here, and I'll go to the final evaluation. So we have the codes here, and I've also given a link that you can follow. And let's go to our final evaluation. So we fit the model. So this is what the model looks like. So we have all the lag values. And okay, let's visualize the predictions and average. Predictions and the actual values. So, okay, so this doesn't really look good. So our predictions are the ones in red, and our actuals are the ones in blue. So, and it is from September 2016 to 2017 July. Doesn't really look good. So we haven't really considered seasonality into account. So there are methods that you can follow to get seasonality. You can use lag terms in VAR. And just to show you how bad the model is, it's 23.2331. So we don't really get a nice fit to the data using this model. And yeah, this is just one way of modeling. And now I'll show you a better method, a different method for time series forecasting. This is also a simple method, but you will get a higher root mean square value. Okay, so we'll move back to our presentation. And now we're going to talk about time series forecasting using deep learning methods. So I told you how to split the data, the first 25 and first 75 and last 25 for testing. And yeah, so the method that I'm going to use now is a very simple MLP model that we saw earlier, but there are some more suitable models like LSTM and GRU. I think it will be covered in the future sections in this workshop as well. And I've also given you links that you can follow for them. And I found this nice library, a recent library that was developed by Facebook Research called a CATS framework for time series forecasting. So they have this easy to use 10 models that's already built in. So you can have a look at that as well. So let's move to our notebook again. And here, so for DF3 training, so for the training set, we get the DF3 train X, and we drop the temperature. And for testing X value, we get the testing data frame, and we drop the temperature again. And for the Y values, we use the DF3 train for the training Y and DF3 test temperature for testing Y. So we get that. And then we fit the data. So similar to what we did with our normal regressions, we use MLP regressor, but we use two different data sets. So, okay, so in MLP regressor, here I use a hidden layer size from 2 to 100 and the activation function to ReLU. And I changed the number of iterations because I tried with like 200 iterations and it did not optimize. So I get the number of iterations to 1000 and I put the verbose to true. So you can see how the model is minimizing its losses. So you can see it with verbose true. And then let's fit the data, fit the model to a training value, training X and Y. Okay, so now you can see how the model is improving. So in iteration 1, it has 2,513. We finally stop here. Okay. I think it's a bit too much. Where is it stopping? Okay, we stop at 2.15 at iteration 536. And then the training loss did not improve. So the model has stopped training. So, okay, then now let's make the predictions. So we call it Y predict. And we predict using our test data set, and MLPTS is the model that we just built. Okay, so now let's make our visualization. It looks good. It stays on a straight line. Let's see it with the time variable. Okay, now it looks really good. It has taken the seasonality into account. It basically has a similar distribution. The predictions and actuals are very close to each other. And looking at the RMSE, it's only 2.18. We have done a nice job here. Okay, so what did we do so far? We fitted 3 models for general regression and for 2 models for time series. And I told you we will be using RMSE for evaluation. And so the model names, we have the model names and RMSEs here. And in general regression, our best model, the one that produces the lowest RMSE, is the MLP regressor, and it's 2.08. And for time series forecasting, we check two models, VAR models and MLP regressors, and MLP regressor is a clear winner here. So we have 2.18. Okay, so now